I'm going to tell you about our system architecture, and more importantly, the rationale behind the architecture and how it's differentiated from other architectures. But I'm going to start with our goals, and Dan touched on some of these. As you mentioned, we are targeted at mainstream applications like Exchange, SQL, VDI. And we realized early on that in order to address these broad set of mainstream applications, we need to build a well-rounded storage system that's efficient on multiple dimensions at once. And in particular, we want to provide both high capacity and high performance at once. On capacity, our goal has been to do better than even the traditional disk-based systems using high-capacity disks. Okay. So today, that translates to something like 30 terabytes in a 3U box, and at a similar price point to these traditional disk-based systems. On performance, our goal is to provide high performance, but not cutthroat performance at the expense of the other dimensions. So this is where we find that some of the other vendors often have built something that's somewhat lopsided. Maybe too much performance, but not enough capacity, or low on some of the other dimensions. Right. Today, we are at 10 times the performance that you'll get from a traditional system. Another dimension we are focused on, as Dad mentioned, is data protection. And our goal here has been to make snapshots and replication so efficient that the user does not have any need to use copy-based backups. So they can use their primary systems themselves to store the snapshots and then to replicate these snapshots for disaster recovery. Data integrity is staple for storage systems. But even here, the architectures vary in terms of how much integrity they provide, to the extent they go to in tolerating various kinds of failures and errors. And our goal here is to be the best in class. We don't want the user to have to worry about the unreliability of either software or hardware. So the user shouldn't have to worry about the fact that flash memory has limited endurance or retention. We'll touch upon some of these later, and they are somewhat self-evident as well. So I'm going to talk about how we meet these goals, but I would like to first step back and discuss the design space of storage architectures in general. And this will help me tell you how our architecture stands with respect to other architectures. So if you look at hardware, you'll find that most storage systems today are pretty much similar. They use a controller or maybe two controllers within an array that control a bunch of drives. Right? And the controller is generally based on general purpose CPUs with multiple cores. The way they connect to drives might be different. They're SATA, SAS, now PCI or NVMe. But in my opinion, that's not a fundamental difference, because most applications are not bound by the I/O bus today. And even if new I/O bus technologies were to become available, as they will over time, it's not that difficult for a storage vendor to adapt to these new technologies. So it's not a sticky point within architecture. Pretty much the only fundamental difference in the hardware is the storage media. Does it use only disk, only flash, or a combination of flash and disk? So clearly, if hardware was all there was to storage architectures, we'll have just three architectures, right? And the reason there are many more is that the software sets them apart. It's most of the differentiation is in the software in terms of how the software uses the storage media. For example, if flash is involved, then does it use flash as a resting place for data, or does it use flash as an accelerator for reads and writes for data stored on disk? And similarly, if disk is involved, there the main thing that matters is how the data is laid out on disk. And that layout also determines what kind of space savings you get. How efficient is thin provisioning, snapshots, clones, compression, dedupe. All of that comes from how the data is laid out. And a final differentiator is how can the system scale, both in capacity and performance. So I'm going to talk about each of these differentiators and the various options there are for each and their pros and cons. Okay, so let's start with the hardware differentiator, which is around what tiers of storage media there might be. So there is still some application for a disk-only storage system, because disk is still the king of capacity by far. Now, it's far behind flash in terms of random I/O. So these systems are pretty much now relegated to applications that need to store a lot of data, but access that data sequentially. Maybe video service and then parts of video service that do not require random editing. On the other hand, you could have a system with only flash, and it would provide consistent performance across the entire data set, because the whole data set would be residing in flash. And in some sense, it's actually simpler to implement than a multi-tier system, because there's a single tier involved, single medium involved. The problem is that flash is expensive. Okay. So an enterprise-grade hard disk, high-density hard disk, is roughly 10 cents per gigabyte today. And the cheapest flash, and I'm talking about consumer-grade MLC here, is about $1 per gigabyte. So that's a 10x difference. Now, one might say that various data reduction techniques can bring down the effective cost of capacity for flash. But one has to keep in mind that of these techniques, compression is applicable to both flash and disk. So that does not change the relative cost of capacity between flash and disk. Deduplication is indeed easier to do on flash for various reasons. But if you look at its incremental benefit over what compression already provides and what snapshots and clones provide, that is pretty limited. And even that's not very dependable. So it's generally less than 1.5x. So there's, even with deduplication, there's still a big gap in the cost of capacity. The third option here is to have a combination of flash and disk, and that holds the promise of providing the best of the two worlds. So you could have a flash tier for your hot data, and a disk tier for your cold data or data that you access sequentially. Right? And this in practice works quite well because most of the data is cold. If you think about email, for example, right? You might hold years of email in your mailbox, but you're generally accessing only email that you got in the last week or so. Or think about snapshots that are used infrequently in case of recovering data only. Right? And there's no need to put snapshots or such cold data on flash. So I'm going to assume that, that this combination of flash and disk has the promise of providing the best of the two worlds, and then look at what different ways there are to use this flash. So the simplest possibility is to use flash as a resting place, as a peer of disk. Okay, so some data would reside on flash and some on disk. And this is particularly easy to implement for the storage vendors, because if they have a storage stack that works with disk drives, it can be made to work with flash drives without much more extra effort. The problem here is that it works well if the workload is relatively static. But if the working set is shifting with time, as it does with email, for example, where it's the last few days worth of email that is hot, then the system has to migrate data between the flash and the disk tiers. And that migration is expensive because it's moving, it's changing the home location of the data. It has to both, whenever it migrates data from disk to flash, it has to kick some data back from flash to disk. That causes extra I/O. And because it is expensive, the systems don't do it very often. They have a very high bar for migrating data. So typically they react in hours or days. And what that means is that if you have a workload that's changing, you are forced to put most of your data set in flash to guarantee good performance, which defeats the purpose of having a two-tier system, because then now you need a larger flash tier. Another mode of using flash would be to use it for accelerating writes, so as a write buffer. And so traditionally, storage systems have used NVRAM for this purpose. And a flash-based write buffer would be similar, except bigger. And therefore, it can absorb larger bursts of writes. Problem here is that flash is not as good with writes as it is with reads. The performance is lower, but more importantly, it has, as you know, limited endurance. And if you are pushing all the writes to flash, it can burn through that endurance very quickly. So the final mode of using flash is to accelerate reads as a read cache. And this is a particularly good match because that's what flash is best at, random reads. It's about 100 times faster than disk on random reads. One advantage of using it in this mode is that in this case, the data on flash is a subset of data on disk. So if there is any loss of data on flash because of limited endurance, say, the system can always fall back to the data on disk. So it tolerates the unreliability around flash very gracefully. Also in this mode, for the same reason that we can tolerate the loss of data on flash, there's no need to have RAID parity, which is a 20% savings. And also, typically systems that use flash to store the only copy of some data need to have some over-provisioning to make sure that garbage collection works efficiently and the right amplification is down. And that over-provisioning is at least another 20%. So you can save all of this by using flash as just a read accelerator. Another big benefit of using flash is that since you can, in this case, lose data on flash, or similarly, you can increase the amount of flash to cache more data, we can easily change the flash to disk ratio. Okay. We still want a bare minimum so that it can store the metadata, because that's a big bang for the buck. Storing the metadata in flash, just 1% of the disk capacity in flash can avoid half the IOs, because half the IOs in general are to metadata. But you can scale that ratio all the way up. So as the cost of flash goes down, you can increase the amount of this cache ratio. Any questions so far?
I think that seems pretty straightforward to a lot of these guys, yeah.
All right. Okay, so the next differentiator then is how to use disk, right? And there are different kinds of layout that different storage systems use for data on disk. The most common layout is what you might call write in place, where each block has a home location, a fixed location within a stripe. Okay, so here I've shown these stripes as these rows, and different stripes may have different logical addresses, but within a stripe, the blocks are laid out sequentially. So it's a relatively simple mapping from the logical to the physical space. But what this means is that if the application is doing random writes, it translates to random physical writes as well. So random writes don't do well. Now, it does support thin provisioning, but at the level of entire stripes. So if the application writes a single block, the system has to allocate the entire stripe, which might be in megabytes. So it's not completely thin provisioned, but because the stripes can be at different addresses, it has some elements. It supports snapshots, but the old style, the copy on write snapshots, where if a block is written, its pre-image needs to be copied out to some snapshot area, okay? Which means that you're doing these copies for every time you write the block after a snapshot. And what that means is that you cannot take snapshots very frequently, because otherwise you'll be doing copying all the time. So a more advanced layout is write in holes, basically writing anywhere there is free space. So this is also known as a write anywhere layout. And this works well initially when the entire system is free, all of the space is free, because then the system can serialize all the writes regardless of their logical addresses into these physical stripes on disk. But over time, free space gets fragmented into smaller and smaller holes, and the system is forced to write into these holes, and thereby, it falls back to doing random writes.
As long as I keep my utilization under 40%, that's fine.
Pardon me?
As long as I keep my utilization under 40%, that's fine.
That's right. That's right. The lower the utilization, the less the problem, but then you lose capacity. Okay, so then there is an even more advanced layout, which is has been known for some time as log structured layout, or writing in large stripes, where the system runs a process often called garbage collection that sweeps the dead blocks into free stripes, such that it always has free stripes to write into. So it's always writing in free stripes. And that has some challenges in that this garbage collection process is tricky to do efficiently, especially on hard disk. Okay. And I believe we are unique in taking this approach among primary storage systems for hard disk. But once you overcome these engineering challenges on garbage collection, the payoff is huge. Basically what it means is that writes are always fast, even as the system ages. And it has a bunch of other advantages. For example, it supports multi-parity RAID efficiently, because the cost of updating the parity blocks is amortized over the entire stripe, since you're writing the whole stripe. Also, since you're writing the whole stripe, the block boundaries within each stripe do not matter so much. They don't need to be aligned, which means this supports variable block size, which is great for supporting compression. So this is the reason why we are able to support compression for all sorts of workloads, even workloads that do random updates. Okay, so this ties together all of the various differentiators that I've talked about so far and shows our architecture. Well, you already know by now we use a combination of disk and flash. We use flash as a read cache to accelerate the reads, and writes are accelerated by virtue of the layout on disk. So basically, it's an architecture that uses the hardware components very efficiently, uses flash for what it is best at, and converts writes, serializes the writes, which the disk can then take quite well. Okay, so the final differentiator I want to talk about is how to scale. And in general, there are two modes here, scale up or scale out, where scale up means adding resources to an existing array, and scale out means adding more arrays, whole arrays, and making them work in a peer-to-peer cluster. And as Dan mentioned before, we support 3 independent modes of scale up. The customer can just replace the controllers, which carry the CPUs and DRAM. And today this allows us to scale our performance by a factor of 2. The customer can replace the flash drives in the system with higher capacity flash drives. And here, today we scale by a factor of 2 to 8x. But this is just a matter of how high the capacities go up to. So as flash drives become available in higher capacities, this will continue to go. And then the traditional form of scaling, which is to add expansion shells, which allows us to scale the capacity of the system. So we have released all of these 3 modes of scaling up. And we are now in beta with scale out, which is this very powerful ability to add whole arrays and scale all the dimensions at once. And the key here is that the scaling here has a multiplier effect on the scaling with these previous modes. So these modes still apply. One would expect that the customer would scale up first, and then when it has reached the limits of that scale up, they would scale out. So whatever scale out provides has a multiplier effect on what scale up does.
Are you going to talk more about how scale out works?
Actually, we decided we would leave that for later.
Okay.
I would tell you a few of the key features there. It's a shared nothing architecture, so each array works independently. The system is able to, so it provides a single point of management. It provides the ability to pool the capacity across multiple arrays, and the user can specify which arrays to pool into a single capacity pool. And the system automatically rebalances the data between the arrays within a pool. And it does it live as the data is being read and written. Each volume is striped across all the arrays within the pool. So what that means is that there would not be any hotspots for either capacity or performance. So a single hot volume can leverage the hardware across all the arrays within the pool, CPU, memory, networking, flash cache, and disk. And finally, the host can connect to all the arrays in parallel and access the data directly independently of any striping. They can go to the array that holds the data, and therefore it scales performance pretty much linearly.
That'll be interesting to see. That's not easy to do.
It's not. It is a hard thing to do, and I believe we have pulled it off.
It'd be useful to point out where you are in the beta as well. Now, multiple customers are in beta with that. We just not GA'd that, Stephen. But
Okay.
it's currently in beta with multiple customer sites.
Oh, so this is not just a slideshow
No, that's
feature.
I think it's literally now.
Yeah.
No, the slideshow was a while ago.
So that's all I have.
I still have to twist Dan's arm about getting in the lab.